Hey guys, in this video I'm going to show you guys how to do spectrum analysis in Multisim, and we're going to use a couple of filter circuits as our examples, like a high pass or a low pass filter. So let's get right into it. I'm going to open up Multisim here, and I'm going to do everything from scratch so you guys can see how this works, and some of this might be good review if you're still struggling in using Multisim. Okay, so now I have Multisim open. I am going to go over and I click on the ground symbol. Doesn't really matter which one you click on because you can always change it in the sources or here under group, excuse me. So when I click on the ground symbol, it automatically takes me to the sources group. And the first thing I'm going to get, I'm going to click on power sources, and then I'm going to select ground. I always go to that first, and then I'll put it at the bottom left corner of my workspace. And then for this circuit, we don't need a battery, so we just need an AC signal source. I can use AC power. That would work just fine, but I'm going to go to my signal voltage sources family, which is here, and I'm going to select AC voltage and put it over here above my ground symbol, like so. Okay, so let's build a low pass filter. So for a low pass filter, I am going to let's see, I got to change my group from sources to basic. And when I do that, this is the group that has all the basic components, such as resistors and transformers and switches and capacitors and inductors and so forth. So I want to get a resistor, so I'm going to click on resistor. And as you've seen me do before, I just simply go ahead and place it. I don't care what the value is at this point. So let's put it right here. And then I'm going to get a capacitor. So I'm going to click on capacitor. And again, I don't care what the value is. And I'm going to put it right here. And that's it. So I'm going to hit close. So I'm done putting components. And now I'm going to draw my simple series circuit. So I'm going to right click on the capacitor and rotate it so that it orients vertical. And now I can draw my circuit. I can start connecting my wires. And just like so. All right. And so this would be, I'm going to move this up. I like everything to look as neat as possible. So I'm just moving that up a tad. Okay, so now I have over here, I have a simple RC circuit, and my output is going to be here. So the capacitor is going to be in parallel with my output. And I have not drawn an output as far as a load resistor, and that's fine. But I do want to go ahead and add an output terminal. I don't need that for what I'm going to show you first, but we are going to need it second, and you'll see why. So to do that, to add an output pin, just go up here to place, and then connectors, and then I'm looking for the output connector. And there it is. So I'm going to put it right here, like so, and then I'm going to connect it up with a wire. And then I'm going to double click on the label, and I'm going to change it from IO1 to just simply called out. And the direction should be an output. It can be changed, but that's what it is. So that's going to be kind of our signal out that's coming from this filter. That would be the positive signal out. Obviously, the negative out would be ground, and we know that that's here. Hopefully, you know that that is there. You could also bring in another ground symbol if you wanted to, but I'm not going to do that. All right, so Let's look at what this looks like on an oscilloscope. So let's go and get an oscilloscope. We've already done this before, so this should be just review. And let's look at the output on the oscilloscope, which would be right here. So you're going to see something very familiar, and you probably already know that this should look like a sine wave. We're starting with a sine wave in. We should be getting a sine wave out. There's nothing in this circuit that's going to change it from a sine wave. Hopefully, we don't have an amplifier. We don't have a diode or a semiconductor that could possibly clip or chop up our sine wave. So let's run it and see what we have. Okay, I'm not seeing a whole lot here, so I got to make some adjustments on the oscilloscope. Change my volts per division. Oh yeah, and then change my time base, because right now we're seeing too many cycles on the screen. There we go. This is looking familiar. Change my trigger to normal. There. So, got a sine wave. And remember now, an oscilloscope shows two parameters of a signal. It only shows two. It shows voltage, which is in the vertical axis, or the vertical dimension is going to be voltage. So we're looking at voltage that's increasing and decreasing. And then on the horizontal axis, what are we measuring there? We're measuring time. So from left to right is time. So don't take that for granted, because we're about to show a different instrument that will give us a different display of the same signal. All right, so this is what 1,000 hertz AC signal at 1 volt peak looks like. Well, it's not 1 volt peak because it's gone through this filter, so we've got some loss here. And we can measure that. Let's see. Let's shift this down, get that negative peak just about there on that division line. See that? And then we can say 1, 2, 3, just a little over 3 divisions. And each division is 100 millivolts. I see that here. So we're looking at about 300 millivolts, a little bit more, 310 maybe, 310 millivolts peak to peak, from the positive peak to the negative peak. And I've measured that manually using the grid on the screen. That's quite a bit less than what we started with, because peak to peak we started with 2 volts. Okay, enough of that. That was review. Let's get rid of the oscilloscope, and let's talk about a new instrument that is going to help us do spectrum analysis, and that is going to be a spectrum analyzer. Now in Multisim, they call it a Bode Plotter, which is basically the same thing. You're probably not going to go out and buy a Bode Plotter nowadays. It's going to be called a spectrum analyzer, but again, it's going to give us the same result. So let's bring in the Bode Plotter, and let's put it right here. And you'll notice, let me drag it over here. You'll notice it has an in and an out, an input and an output. You think that's an output, but it's really not. Both of these are inputs that come into the Bode Plotter, but it's kind of telling you that it needs the input signal here and it needs the output signal here. And then there's 2 positive terminals and 2 negative terminals. Those negative terminals, go ahead and tie them to ground, both of the negative terminals, and you're done with those. Just like that. Next, we need to take the positive terminal for the in and connect it to our input signal. Where is our input signal? It's here. That's our input signal. That's our source. And let's move the wire so it'll look a little better. And then finally, our output signal needs to tie to the out, like so. And just straightening up some wires, moving them around. And that's it. So that's our Bode Plotter. That's how it hooks up to the circuit. We find out whatever the signal is we want to look at and measure, and we put that to the out input on the Bode plotter. And then the in input on the Bode plotter goes to our signal source, which in this case is right out of the what would normally be a function generator. But in Multisim, that's our AC voltage source that's located here. All right, now let's double click on the Bode plotter and open up the window. And notice that it looks very similar to an oscilloscope. It's going to have a screen that'll have a grid on it, and it'll have a x-axis and a y-axis, except a spectrum analyzer does not show voltage versus time. It shows voltage versus frequency. Big difference. And you're going to see that the screen is going to look completely different. So we've also got to come over here and make some changes to our settings. So let's change. And right now it is set for a frequency range of 1 gigahertz with a resolution of 1 millihertz. And that's quite a bit extreme for what we're doing here. So we're going to change the frequency resolution to, let's do 1 megahertz. That's still really large for what we're trying to measure here. But I think that will work. And then let's change the resolution to 1 hertz. So 1 megahertz and 1 hertz. Now this is something that we might have to tweak or fine tune after we run our circuit here. That's the horizontal scale. That's, in other words, the frequency range on the screen. Next is going to be the vertical axis. And on a spectrum analyzer, or in this case, a Bode plotter, on a spectrum analyzer, your vertical axis, even though it's voltage, they normally show you the measurements in decibels. Because in a lot of applications in using spectrum analysis, we're looking for gain or attenuation, which is most of the time measured in decibels, not volts. But it's still magnitude, or it's still, the more voltage of a signal we have, the more decibels you're going to have. So they're related to each other. So don't let that throw you off. And let's see. Right now, it's got a 0 dB max and then a negative 200 dB minimum. That's way too. Let's do negative 100. That's negative 100 decibels. And 0 dB would be at the top. And let's change that. And I'll show you why in a second. Let's change it to 10. So 10 dB at the top to negative 100 at the bottom. Or let's do negative 90. That gives us a span of 100 decibels from top to bottom on the screen. But again, not extremely important in that. We may have to tweak these numbers. And I think that's it. I think that's all we have to do here. Let's hit the run. And boom, look at there. Now we can hit stop. Don't have to leave it run. You can leave it running, but there's really no need to, because we may want to make changes. And look at what we've got on the screen. We have the frequency response of a low-pass filter. So a low-pass filter, by design, passes low frequencies, but attenuates high frequencies. So what does a Bode plotter or a spectrum analyzer tell us? Or what is it showing us? It's showing us a response of the circuit. It's showing us amplitude in decibels based on frequency. So let's look at the cursor. Let's move the cursor around. The cursor over here on the left, and we can see what frequency we're currently at. We're currently a little above 1 hertz, and then we have a value of 0 dB. As we begin to move up in the circuit, you can see that now we're at about 10 hertz. And the signal has gone down just a little bit. Nothing really detectable by sight or ears or in the real world, going down negative 0.018 dB is really nothing. So it hasn't really gone down. And you'll notice just by looking, at some point it begins to start to fall, like so. And then it looks like it begins this descent. So as I go up in frequency, which is what I'm doing now, and you can see what frequency we're currently at, you can see that the output in decibels is now much lower. So we started out at 0 decibels, and now we're at negative 61 decibels. You can change that. I mean, I don't know if the Bode Plotter here lets us do that. And it doesn't. It's going to keep the answers in decibels. But on some spectrum analyzers, it'll allow you to see the answer in voltage or, you know, some other magnitude. But decibels is by far the most common. So right now, let's get to an even number or close to an even number in frequency. And it's hard to with the mouse. So let's just say that this is about 200 kilohertz. So at 200 kilohertz, the output of this circuit is 62 decibels below what it was back at the lower frequencies. So it's attenuating the signal. It's attenuating the sine wave. In other words, the sine wave's amplitude is dropping as the sine wave's frequency increases. So we get a all-in-one look or an overview or a spectrum view or a spectrum analysis of the response of this circuit. So we can determine a lot. I mean, if you did not know this was a low-pass filter just by looking at the arrangement of it, well, now we do by looking at the spectrum view or the Bode Plotter view or the spectrum analyzer view. Oscilloscope didn't show us that. It can, but on oscilloscope, we would have to put in different frequencies over here. And we did that, I think, the other day. I showed you an example of that where we put in a frequency, look at the voltage on the oscilloscope, then put in a higher frequency, and then you saw the voltage on the oscilloscope go down. So that's giving me a hint that as we go up in frequency, the output voltage is going down. So that is the characteristic of a low-pass filter. It passes low frequencies. In other words, down here, these frequencies are not being attenuated. But high frequencies are. And the higher the frequency would go, the more the attenuation. So it's not a steep or an instant cutoff. Okay, so that's how we use the Bode Plotter. Let's make some changes. Let's change this back to 0. And then you can see what changed. Notice that the red line is now at the very top, which is okay. That's perfectly fine. I like to have a little headroom or padding above the waveform, but that is completely fine. If we left this at negative 200, you can see there that we're not seeing as much of the red on the screen. So we're not getting the best reading. So we want to adjust these numbers. Let's go to negative 50. And you can see there that it doesn't change the reading. It just changes the resolution on the screen. Now it's cutting off before it gets to the end of the screen, which is okay. But again, you can tweak these numbers to get the screen to look like you want it to. So I put in 10. So that means the top line now is plus 10 or 10 decibels. They've put in a 0 line for us, this dotted line here. And then as we go below this, we start going into negative decibels, or that's really decibels of attenuation. Going up would be decibels of amplification, but we don't have an amplifier, so we're not going to get any signals over here greater than what we started with. All right, so that is a little bit of an introduction on how to use the Bode Plotter, which is Multisim's version of a spectrum analyzer. All right, so let's close out the Bode Plotter and let's get rid of it. Now let me show you another way. We got a ground wire here hanging on. Let's get rid of it. Now let me show you another way to do spectrum analysis in Multisim without having to use any of the test equipment over here. You see up here in the window where the run button is, you'll see where it says interactive. We can click on that, click on interactive, and now you have all of these analyses that you can do on the circuit. By default, we leave it on interactive, and that's where we can bring over test instruments or multimeters and function generators, oscilloscopes, the Bode Plotter that we just used. We can put those in the circuit, run the circuit as if we were doing this on a real circuit on the workbench. But there are many powerful things that Multisim will do kind of on its own and not interactive. And one of those is spectrum analysis. So let's go down to where it says AC sweep. That's what we're going to use to do spectrum analysis. So let's click on AC sweep. So we're changing from interactive to AC sweep. And you'll notice that we have some settings here. Frequency parameters. In other words, the start frequency and the stop frequency. Sometimes you don't know what frequencies you want to start and stop at. So they're kind of giving you a suggestion, or kind of the maximum probably here, which is way too wide of a frequency span. So again, we don't have to go to 10 gigahertz. So again, let's make this 1 megahertz like we did before. 1 megahertz. We'll start at 1 hertz. That's fine. The sweep type, we're going to leave it at the default setting, which is decade. And the number of points per decade, 10, we're going to leave that. Excuse me. And the vertical scale, we're going to leave it as log. And okay, so then let's go to the output tab. This is very important. This is why I had you guys to add earlier the output connector. This makes this part very easy. Now all you have to do is go down the list of the variables in the circuit, and you can see that we have several. We've got a I, P, 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 V, V. So I stands for current, P stands for power, V stands for voltage. The current through C1, the current through R1, the current of V1, which is the voltage source. The power of C1, the power of R1, the power of the voltage source. V1 is node 1. Don't worry about that. And then V out. This out, whatever is in these parentheses, is going to match the name that we give that connector. So it's very important that you know the name of your connector. That's why I renamed it to out. So I would instantly know that, hey, that's the connector I put in there. So you want to highlight that and click add, and that'll bring it over to the right side of the screen. And this is the selected variable for analysis. This is what we're going to analyze, the output voltage. And that's all I need. I don't really need anything else that's in this list, regardless of how much shows up here for your circuit. The more components you have, the much longer this list will be. Okay, so analysis options, let's look at that. We're not going to change anything there. Summary, don't worry about that. So let's go back to output. Yeah, I don't see anything there. Frequency parameters. And then we can hit save, or we can just go ahead and hit run. Let's hit run. Look at there. All right, so now we have a grapher view that has popped up. And if you'll notice in the grapher view, it is showing us, and I like to make this a little bit bigger to get a, so I'm just going to drag that window. There we go. And now you notice that it's showing us two graphs. The bottom graph, don't really worry about that at this point. That's for another day. The top graph is a magnitude graph or amplitude, kind of the same thing. So it is showing us basically the same thing that the Bode Plotter showed us. It is showing the frequency response of our circuit, which we can quickly look at that and say, hey, that's a low-pass filter. I know that's a low-pass filter. And you can see that lower frequencies, we start at 1 hertz. and we go all the way up to 1 megahertz. And this is a log scale. That means that the frequencies are not evenly spaced. And if you look at the real carefully, you can see the little tick marks down here on the scale. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. So if you remember from math class, hopefully you've had a math class where you talked about logs or the logarithmic scale, and it's not an even dispersion along the graph. But anyway, so you can see here on the left, the vertical axis, this has a magnitude of 1. Magnitude of 1 means that whatever came out equals whatever came in. So we don't have any attenuation or amplification going on until we get here. We can start to see that we start to go under values of 1 for magnitude, and then the circuit begins to drop. We can come in here and let's see, we can right click and we can do different things. We can change trace width, we can change trace color, data point shape, hide, copy, delete, show, hide traces, trace properties, that type of thing. So, so we can get some measurements here. Cursors, can we put a cursor here? I thought you could. I may have to do a little research on that. We can show grid. Oh, show cursors. There it is. There we go. So we got a cursor window that's popped up, and cursors have been applied. There we go. So now I can place a cursor. This is cursor number 2. And I can come down here and I can look at the values associated with cursor number 2. It's actually showing me both cursors. So be careful. Make sure you're looking at the data for the correct one. X1, Y1, X2, Y2. So that would be the x-axis, the value at the x-axis at cursor 1. So cursor 1, x-axis would be, let's see, let me put it on the first tick mark, which is close to there. So you can see that it says 2.0461. So we know that the x-axis is measuring frequency. So that's going to be 2 hertz, or a little bit over 2 hertz. Cursor number 2, it's up here, and its X value is 24.3531. And we know that it's in hertz because it tells us that here on the graph. The Y value at cursor 2, that would be Y2, is 988.3718 milli, because it's just below 1. Remember, it dropped down just a little bit below 1. Cursor number 1 is currently sitting at 999.9164 milli. So if we know what the voltage was coming in, we can basically multiply it times this magnitude value. In other words, so I would convert this to like 0.999999164 as far as my magnitude. So it's not giving you actual voltages, and it's not giving you decibels, not on this screen. It's just giving you a magnitude, and you have to multiply that magnitude by whatever the input was. And then as I bring that cursor over, let's bring it over to 1 kilohertz, which is somewhere close to there. Oh, yes, exactly. I did pretty good on that. So cursor number 2 is sitting at exactly 1 kilohertz. And at 1 kilohertz, the magnitude, so that would be Y2. Y2 is 157.1767 M, or milli, which is the same as 0.157. So if we started out with 10 volts coming in, as an example, then it would be 10 times 0.1571767, and then that would give you your output voltage at that frequency. So that's what this is showing us. So that is how to use spectrum analysis using the AC sweep function in Multisim. Notice back up here where it says run, now it is in AC sweep mode. And if I hit run, it's not going to operate the circuit like it did when we used oscilloscopes and stuff, because you would have to change it back to interactive. So if I hit run again, it's going to bring up the graph review and it's going to show us what we just did. Also, the graph review remembers everything that you've done. So if you look at the tabs up here, that was the AC sweep we did before. Look at there. There's a Bode Plotter and there's an oscilloscope view. So anything that you capture as far as visual data or graphs from your circuit, it remembers those and stores them here in the graph review. So this is a good place to go back and grab some screenshots if you needed to, that type. And you can close these. If you don't want them, you can actually close them. I think you hit X maybe. Yeah, delete graph page. So like we can hit X here and it gets rid of that. It didn't get rid of the tab. There it goes. It went that time. All right, so let's get rid of that one. There. This seems like it's a two-step process. I don't know if that's a bug or what. So be careful with that. Don't delete anything you might need later. Okay, so one more quick thing. Let me reverse. Let's get rid of that. Let's get rid of those wires. And let's do this. I'm just swapping the position of the capacitor and the resistor. And some of you might know what type of circuit this makes just by doing a quick swap. And if you don't, I'm not going to tell you. We're going to see. Getting everything looking neat. We're still in AC sweep mode. We haven't changed anything other than I've swapped the position of the capacitor and the resistor. So now the capacitor is in series with the output and the resistor is in parallel with the output. So let's hit run. Look at there. So what type of circuit is this? Notice the graph is different. It looks like it's reverse directions. This is a high pass filter. All I had to do was change the position of the resistor and the capacitor. And now I've created a high pass filter. High pass filter means that high frequencies, which are these up here, are allowed to pass with very little, if any, attenuation. That means low frequencies are attenuated. They're reduced. And the lower the frequency, the more attenuation, or the more that the signal has been reduced to the output. So we have a low pass, we have a high pass filter circuit. And I quickly just determined that using the AC analysis. I didn't have to go in and I didn't have to get the oscilloscope. I didn't have to do a bunch of measurements. So we know all that. One last thing, since hopefully you've talked about filters before. If not, we're going to be covering it in the ELN 132 class, if you're in that class. I'm going to duplicate these parts. I'm copying and pasting is what I'm doing here, like so. Not going to give away all the information here, but we will talk about this particular circuit. But let's see what changes. So now I've just basically got two capacitors and two resistors. Looks like the capacitors are in series. Looks like the resistors are in parallel to some degree. Let's run this again. And you can see that we still have what type of circuit? We still have a high pass circuit. but it does have some different parameters. And I can go back and forth. Look at there. So this is the one we just did when I added the two components, and you can see the graph. And then this one, this tab would be the one we did right before. And they don't look majorly different. But if you start doing some measurements on these two, you will see there are some big differences between the two. For example, cursor number 1 on the circuit we previously did, the Y value is 17 milli. On the circuit we just did, when I added the two more components, the Y value is 295 micro, which is 0.295 milli. So 0.295 milli versus 17 milli. Quite a bit of difference in the attenuation down here in the low frequencies. So again, we'll talk about that later, and advantages and disadvantages of what I just did by adding two more components. But hopefully this will get you started to using some spectrum analysis tools in Multisim, using the Bode Plotter. Remember, the Bode Plotter is over here. There it is. And or using the AC sweep analysis, which is located here when you click on interactive. Now we can always go back to interactive. Just simply change that to interactive and click save and make sure it says interactive. And now you can bring over an instrument and you can do some measurements and run the circuit to make your measurements. That's interactive. I can go back to sweep and make sure my parameters are set correctly. Make sure I have an output that's been chosen, and I can save that. And then I can always just hit run here to get an analysis, an AC sweep analysis. It's called sweep because the way this works is they actually start out, and they do all the hard work for you, where they start out testing at the low frequency, and then they change to a next frequency, then they change to the next frequency. And so it's like a sweep. They start low, and it comes up high and sweeps all the way up to the high frequency and then starts over. And it does that over and over and over, and then we get our measurement. So in case you were wondering, that's why it's called an AC sweep. But it is a spectrum view and a spectrum analysis of what's going on with our circuit. Well, I think that's enough for this video. That should get you started and help you in doing a couple of labs where we're going to have to use Multisim to analyze our circuit and find out what's going on in the spectrum of that circuit, as far as how does the circuit behave with different frequencies. That's the whole purpose of this. One last thing, it really doesn't matter for what we're doing with the Bode Plotter and the AC sweep analysis. It doesn't really matter what this input frequency is set to, because it's really not using that. So don't worry about too much. Notice that I put in the AC voltage source, and I'm just using its default value of 1 kilohertz, and I didn't change it. So no need to change that for what we're doing here anyway. So if you have any questions, let me know, but that should hopefully answer the basic questions on using AC sweep. Don't forget to go back to interactive. I said one last thing. Let me show you one other thing. This is a common error you might get. So let's hit save. I'm set to AC sweep. Now hit run. Now it's giving me an error. It's not giving me the results we got a while ago. The active analysis produced the following error. There are no valid output variables. And reason is under the output tab, we have not selected one of the variables here and put it over here in the selected variables for analysis column. You got to have something over here in this column, and it needs to be your output. That's the reason that we created that output connector. So grab that, hit add, and that's it. Then hit save. Now when you hit analysis. Let's get rid of that cursor window. Now you get it. It works. So that's an error message that I'm sure somebody's going to run into. And go back to the beginning of the video if you need to know how to add this output here to the circuit. All right, guys. Well, that takes care of at least this introduction. We will talk more about it in an online lab. So see you then.